Hello, hello. Hi, everyone. We're going to wrap up Unit 1 today. So let's get started right away. So we're going to do integrations. Sorry. We're going to do integration by substitution. So the idea of substitution, there's several. Um, there's, I think there's three, but the two I like the most is, well, you have to recall chain rule. And the first tidbit is what substitution makes a problem easier? And then the second one is what product of a function and its derivative do I see? Because the whole point of you using substitution is you're basically going to be using the idea of chain rule. Because when we do a function that has chain rule, it looks very different after it comes out of it. And maybe this one doesn't look that different, but for something like here, we're going to see a big difference, and here. But let's go ahead and just have these as the back burner and do these. So for example here, we don't necessarily see a product and its a product of a function and its derivative, but we do see how if this would be easier if this problem was just e to the u. So, or e to the x, I should say. So I'm going to use u and make it as 2x. But you have to do derivative of this, so you can replace dx. Well, you do du over dx is equal to 2. And then, because of this notation, we're going to abuse it and just multiply, I say in air quotes, by dx to get du is equal to 2 dx. In that way, I'm getting highlighters. Highlighters. I don't know if you got that joke. Well, whatever. Um, 2x is going to be replacing this. I mean, u is going to be replacing that 2x. And then that, we don't exactly have 2 dx there. So what do we do? Well, we know we have dx there. We can rewrite this problem to where it just includes dx. So 1/2 of du is equal to dx. And we'll use that to just replace dx. So this becomes 1/2 integral e to the u du. And keep in mind you use it for this guy and for this guy. Okay. Then we know the integral of this. This is just EU. EU and then plus C. And then you're going to go ahead and plug in back your original U. We use 2x. So E2x plus C. And that would be your answer. Now, granted, if you ever feel like you did this incorrectly, the step I encourage you to do is do the derivative. We know integrals are just backwards derivatives, and derivatives are backwards integrals. So you can go ahead and do a derivative to get this inside. So let's do it. If we do derivative here, it's 1/2 e to x times the derivative of what's inside that, which is just 2. And then any constant will just become up to 0. Simplify this to be e to x, and look, that's what we got. So keep that in mind. All right. Here, let's see. We know that ln is 1 over something, so we can just turn this whole thing into that variable. But we have to do the same thing to the dx, and then you rewrite it like this. Here. I'm going to go ahead and I have this paper. I'm going to cover this so I don't cheat, because I think I accidentally cheated right now, but we'll see. Wait, I do need the highlighters though. Okay, so that's going to replace this. That's going to replace this to give me 1/2 of. Oh, there was an easier way to do that. Oh, we'll talk about it later. 1 over x, or 1 over u, excuse me, du. So then from here, we can go ahead and just rewrite that to be 1/2 ln of u, then plus c. And then we replace u with 2x, because that's what we had initially. And that would be our final answer. Okay. Let's see, a couple of things here that I see for starters. Um, hmm. Let me see what the answers are here. If it comes to me, I think I forgot what I want to here. If it comes to me, I'll go back to it, but right now we're fine. Okay, over here, again, we're gonna do that step 1 where it'd be easier if that was just one variable. So we have u, 8x, du is equal to 8 dx. And then we don't have 8 dx here, we have a dx, so let's just go ahead and divide by 8. So 8 du is equal to dx. And we're going to replace that 8x with the u, and we're going to get rid of dx. The goal with the substitution is that we want to erase every trace of x, so when we do it, we can do it a bit more streamlined. Because there's no point keeping the x in this notation if the whole point is to do substitution to make the problem easier. So we have 1 over 8 sine of u, and then du. So we know that's going to be 1 over 8. Put the negative in front. Cosine of u plus c. And then I plug in back u. Cosine of 8x plus c. Okay. All right. Next, let's see. We have 3 times the square root of 4x. Again, for here, we could technically just replace the 4x to make it just a square root, and then the 3 can just escape by itself. So we do u 4x, du is equal to 4 dx, and again, we don't see 4, so we have to work around it. And we have 3 integral square root of u dx. Oh, and don't forget to, I forgot about adding that part over 4. Okay, let me go ahead and highlight. So again, you use this to replace the 4x, and you use this to replace the dx. So here we have 3 over 4, and then the integral of that is u to the power of 1 over 2 plus 1 over 1 over 2 plus 1, and then plus c. For that, I'm definitely just going to rewrite these as 3 over 2 and 3 over 2. We could cancel out the 3's, and I can rewrite that as a proper fraction to get 2 over 4 u to the power of 3 over 2 plus c. And we know that could just be 1/2. So 1/2 u 3 over 2 plus c. And then I need to plug in back u. 4x 3 over 2 plus c. I think I'm gonna politely, let's see. Okay, good. So it is, oh, I realized 1 over 4 and it was 1 over 2. Okay. Okay, let's keep it moving. Now this one. So this is going to be a thing I told you about, where technically speaking, you're seeing the derivative of one thing as a product next to the other thing. So we see that the derivative of this is 6x squared. And although it's not directly here, with the manipulation of the coefficient in front, it could be there. And then we also see that this whole thing makes it cumbersome. And we know that we can sneak, or not we know. I'm telling you that you can sneak in a constant into this. The reason why we choose to sneak in a constant is because we know that the derivative of a constant will just disappear. So it was snuck in. And then we need to rearrange this a little bit. Let's do the dx on the left-hand side. And then we have 4. So we have two choices here. We can make it to where it's 4. We can just only take the x squared when we're substituting. I'm going to only take the x squared when we're substituting. Now from here, use this to replace all of this with a u. And then we'll use this to get the x squared and the dx. So at the moment, we're left with a 4. I'll throw the 1 6 in the front already since it's a constant. And then we'll do u to the power of 4 du. Let's throw in the 4 outside now to be, we'll simplify that to 2 over 3 integral u4 du. And then you get 2 over 3 u to the power of 5 over 5 plus c. We can simplify this a little bit to be 2 over 15 and then u to the power of 5 plus c. And then we're going to go ahead, I forgot boxes. And then we're going to go ahead and put back u. 2x3 plus 1 to the power of 5 plus c. And let's see, a little different looking, but we basically got the same answer. Okay. All right. So does that mean you have to do substitution all of the time? Not necessarily. Okay. Because sometimes you can get away with recalling certain aspects of the substitution. So, let me show you the one I saw over here. We know that via distributive property, here, I'm going to do it in an erasable pen. So if you're taking notes with me, make sure it's something erasable. You can technically split that up to be 3 times 4 squared times x squared. And then we know that's just going to be 2, so that's going to be 6 integral square root of x. And then dx. From there, we know the integral, which is going to be 6 times, what was it, 3 over 2, so 2 over 3, u, 3 over 2. This simplifies to a 4u cubed, or not u, sorry, x. And let's see. So it doesn't look exactly the same, but it is basically the same because we know if we went over here and we factor out the 4, 1 over 2, 4 to the power of 3 over 2, x to the power of 3 over 2, this it's just going to be 8, and then 1/2 of 8 is 4. So you do get the same answer, but this is still just a neat way for us to practice and keep going with these. Um, to be transparent with you, there's another one that I see, but I want to double check my math because over here, I know that I can technically factor out the 1/2 integral 1x dx. So then from here, I know that's going to be 1/2 ln of x and then plus c. But obviously, this in no way equals that. So I was thinking, mm, oh, I know what happens. Oh, that's so annoying. Okay, I can see what happens here. So what happens here is that when you use log rules, I guess a quick recap of log rules since I'm in this territory now. If we have log of A plus log of B, that could be rewritten as log of A times B. If it's subtracting, then it's subtracting. If you have log, or let's say C times log of A, that could be written as log of A to the power of C. Okay, and then from there, what you have is that this can technically be written as, here, I'm going to erase, I'll erase it a little bit. This can be rewritten as 1/2 parentheses ln of 2 plus ln of x. Now the gimmick with the constant is that this ln of 2 term can technically be absorbed by the constant, since the constant is just supposed to be a numeric value that is not dependent on a variable. So you would have 1 over 2 ln of 2 plus c. And then this whole thing can technically be written as a new constant. So that's why they don't look equivalent, but they are technically equivalent with the inclusion of the constant idea. Okay. But that's not the point of this lesson. I'm sorry. If this sidetracked, I hope you can rewatch these last minutes and remember the point of this lesson, because the point of this lesson was substitution. But the just to be honest, the nerd in me couldn't help but see the technicality. Okay. All right. Oh, we have more. Perfect. So we're just gonna go back into it. All right. Here, I see that the derivative would be, or the integral would be easier if all this was one variable. But I also see that the derivative of this is kind of there with the constant missing. So I'm going to abuse that trick again. We have u is equal to 4x squared plus 1, and we know its derivative is 8x dx. Take out the 8, 1 over 8 du is equal to dx dx. And again, we're going to use, here, I want to cover this up again, because I feel like maybe I'm cheating, or visually you all could be, not cheating, cheating's a strong word, especially in academic sense, right? We could accidentally just be using the left-hand side. There's no other way to say it, really. Like that. And then this, use the x and the dx. 1 over 8 integral 1 over u squared dx. At this point, if you want to, you can rewrite that as a power u negative 2 du, excuse me, du. And then that's just glorified usage of the power rule. So u negative 2 plus 1, which is negative 1, negative 2 plus 1, which is negative 1. And then we can simplify, plus c, simplify this a bit to get negative 1 over 8, 1 over u, and then plus c, then we plug in the u. Negative 1 over 8, 1 over 4x squared plus 1. All right, let's double check if that's the answer. Yeah, pretty good. Okay. All right. Oh, I forgot the plus c. All right. Tangent. Let's go ahead and do tangent. So what variable gives us tangent? Well, this one is a little bit tricky because tangent is not any derivative or any derivatives result. But we know that tangent is technically sine of x over cosine of x. And you could argue that these are derivatives of each other, but you don't know what derivative is of each other, right? Because, well, do I take u to be cosine or u to be sine? Well, you have to remember that, or actually, let me just show both. Here, and I'm going to show both in a erasable pen so that way you can't get spoiled to it. I don't know if you noticed this about me, but I love like having colorful pens. Okay. If I did u to be sine of x, then du has to be cosine of x dx. Now the gimmick is that cosine appears here, but it appears as 1 over cosine, which is not the same thing. You can't, it says cosine, but on the top, over an imaginary 1. However, if you did u to be cosine of x, du would be negative sine of x dx. Sine does appear, and we can make that numeric constant just appear out of brute force, kind of like what we're doing with all these numeric constants. So therefore, you should look at both of them and be like, well, cosine's not on the top, so u would have to be cosine. So we have u to be cosine of x, du to be negative sine of x dx, and then you can just get the negative on its side. And you would replace cosine with u, and you replace both sine and dx with a negative du. So you have negative integral 1 over u du. That's just a negative ln of u plus a constant, and then you plug in back u, cosine of x plus c. All right, very good. Similarly, you see that although sine of to the power of 3, its derivative is not here. You do see that sine's derivative by itself is there. So sine, if we take it to be u, du would be cosine of x dx. And for this one, we kind of don't even really need to manipulate it much because we can just see that cosine and dx are just there plainly. So the integral of u to the power of 3 du. Then from there, you can use a glorified power rule, and you'll get u to the power of 4 over 4 plus c. And then you plug in u, sine 4 of x over 4 plus c. Yes. All right. Let's move on to 17 and 18. Let's go with 17. So 17 is this integral. We have the luxury of, you can either do it all in one go, or you can split it. I'm going to split it. And then I know that guy already is going to be x plus c, but this guy needs a little work. Okay, I'll call it c1 for now. All right, so let's make u 2x and du be 2 dx. We don't see 2 dx here, so we have to make it work with this equation, and we definitely can. So this gets replaced with u, and then this dx gets replaced with a 1/2 and a du. We have 1/2 integral, and then we have cosine of u du. Then from here, we know that we can take the negative, or not take negative, take the cosine with the negative 1/2 and rewrite that as first the initial part, and then negative 1/2 of sine of x. I'm sorry, sine of u, not x, and then plus c2. We need to plug in back the u. To get sine of 2x plus c2. And then, because we just have two constants willy-nilly here, we can just combine them into one mega constant. And that would be the answer. And don't forget the logic I said out loud. We're combining these two constants into just one mega constant. Now, granted, from here, right, we don't know, like over here, if we have the right answer. What we talked about within this lesson. How could we get the right answer if we needed it? We do the derivative. So the derivative of x, 1. The derivative of this expression, negative 1/2, cosine of 2x, and then the derivative of what's inside of it, which is just 2. So this would simplify to a 1, and then we get 1 minus cosine of 2x. Oh, I forgot to write plus 0, but we can see that pretty straightforward. And it does indeed match. We're going to increase the difficulty just a little bit, where we're going to go ahead and include boundaries, and we're doing a definite integral now. Not too crazy of difficulty, but we can still do it. Within here, I see the substitution should be 2x squared minus 3, because its derivative slightly appears over here, 4x. And we can, dx. Then we can manipulate the 4, 1 over 4 du is equal to x dx. So using this, we can replace all of this with a u. And then using this, we can play x and dx. 1 over 4 integral negative 1 to 0 of u to the power of 5 du. Then from here, we're going to use that power rule. 1 over 4. And then I don't have to include the plus c anymore because we're doing a definite integral. U to the power of 6 over 6 from 0 to negative 1. When I take it to be 0, I'll have 0 by my right in full. And then when I have negative 1 to the power of 6, that's going to come out to be a 1. So let's go ahead and write in full. We have 1 over 4, that's a 0, and then negative 1 over 6. That gets simplified to negative, I don't know why I was going to do it on top, 1 over 24. I was going to do 24 on the top for some reason. All right, and that's the answer. Now, you can't really double check your work like you would before in, hold on, this pet's not working. You can't really double check your work like you did before in the other one, but you could still, at this middle, check your work by doing the derivative. Oh, I made a very easy mistake. Can somebody tell me what mistake I made? No, you can't, because this is a video, it's recorded. Um, I forgot to replace u with its x's. So I definitely need to fix that. Um, hold on, let's see, what should I guess I'll write out the whole thing. And then maybe by the time it dries, I can use this page anymore, but I'm not sure. Oh, it smells bad. Okay. Right now we plug in back here. So 1 over 4 in parentheses 2x squared minus 3 to the power of 6 over 6. 0 and negative 1. Alright, if we plug that in to be 0, okay, we get 0 minus 3 to the power of 6 over 6. And we plug it to be negative 1, we will get 2 minus 3 to the power of 6 over 6. Um, kind of don't like that we're gonna do 6 to the, or negative 3 to the power of 6. I mean, we can, but I probably wouldn't give that question on a test. Here, because we can, because we're doing it in class. Well, yeah, we're doing it in class, right? Let's see. Negative 3 to the power of 6. So 7 to 9 over 6. And then just minus 1, because it's going to be negative 1. Now it'll still be positive 1 over 6. So we'll have 7 to 8 over 6. I'll check if they're divisible. They're probably not going to be exactly divisible. Well, they might be. Uh, I'll simplify it by just dividing both sides by 2. Let's see. So we have 1 over 4. And then we have 364 over 3. And I could technically divide out another 2. So I have 1 over 2, 182 divided by 3. And then I could divide out another 2 to get, I think that's going to be 91 over 3. That'd be the answer. A little ugly looking, but still a valid answer. And again, at this point, you can't really double check this, but you can go here and double check that. And you definitely should see that because a 6 will go in the front, that'll be written as 5, and you do derivative inside, that's 4x. And now simplify the x. So it is true that that's the answer, but I mean that's the integral, the antiderivative, but I digress. All right, in a slightly similar vein of using substitutions for these next 2 pages, we're going to go ahead and use substitution, but with the idea of logs and exponentials. So again, this is sort of a glorified review ish a little bit because remember derivatives are the backwards of integrals, but we don't see that as directly here, so keep that in mind. Here we see that this would be easier if that was just a one single variable, so we're going to make it one single variable. du is equal to 3 dx. And then we don't see a 3 here, so I'm just going to take it out of that equation so I don't have to worry about replacing it. So that will be replaced with the u. Now be replaced with a 1/3 du. So we have 1/3 integral 5 eu du. And actually, I could technically take out the 5 as well. 5 over 3 integral eu du. And that becomes EU plus C, and then plug in back the U. Okay. All right. Next here we have U is 2x, so du is 2dx, 1 over 2 du dx. Again, you're only doing this because there's not a 2 present there. Granted, you could make a 2 appear there if you did something like 1 is equal to 2 times 1 over 2, and then rewrite it there, but I don't like this. This is a trick that really is, it's not, I mean, you can still use it. It's just, I don't know. You should use it when you have to, I feel. Okay. I should just leave these uncapped. Actually, I forgot to highlight this one as well. That gets replaced with u, and this gets replaced with the 1/2, and then dx. So negative 1/2 EU du is equal to negative 1/2 EU plus c. And replace that u with a 2x. Here, difficulty increase. Now not only are we getting indefinite integrals, but we're also getting this sort of nonsense of the x's included. But we can see that this derivative is almost repeated here. So if I do u, 3x squared, its derivative is 6x dx. Now, technically, I only have to divide both sides by 2. You could divide the whole thing by 6, but I'm going to take advantage of that and divide both sides by 2 to get 3x dx. I'm replacing the 3x squared with u. I'm replacing the 3x dx with du. 1/2 from 0 to 2. EU du. Plug those back in. EU to 0, but don't forget the replace the u. E3x squared. 2 and 0. So putting the 2, that'll be e to the 12, and then minus e to 0, which is just a 1. And that would be your answer. Okay. Let's see. I forgot to highlight this again. Okay. Similar vibe here. We got u is x to the power of 3, and du is 3x squared dx. Divide both sides of this equation by 3, so we don't have to worry about finding a 3 to replace. We just take the x squared and the dx, and we just take this to be 1/3, 0, 1, EU du. EU 1, 0, and then we plug in back u, which is just ex third. X to the power 3 and x third. Okay, and then we just plug those in. We get 1 over 3 e minus 1. Because e to the power of 1, that's to the power of 3, is just a 1, just e by itself. And then we know anything to the power of 0 is just going to be 1. Alright, let's move the difficulty. So we see that if this was all just one variable, that'd be a lot nicer. So u, x plus 1, du is just dx. I'm going to take out the negative 3 first so I don't have to worry about it. Then replace the whole thing with the u. 1 over u du. And I get ln of u from 3 to 1. Plug in back to where we're using the x. And then we plug in 1 and 3 respectively. We'll get -3 times ln of 4 minus ln of 2. Okie doke. We keep going. This is definitely just us using the derivative. Du is equal to dx. Place the bottom with the u. And place the dx with du. So, actually, I'll do both in the same step. 1 over u du. 2 ln of u, 6 to 4. And then we plug in the u back, so it's a term of x. And we know that it's going to be 2 parentheses ln of 3 minus ln of 1. Which from there we can just take a shortcut because we know ln of 1 is 0. It'll just be 2 ln of 3 as our final answer. Alright, so now we've had pretty easy derivatives here, but we do see an increase because now there's a row x on top of these guys. But hopefully we should see that taking the derivative of these will make these guys pop out. So for example, if I do for this one, u is x to the power of 3 minus 1, and I take that derivative, I'll get, so I'm going to write it like this first, I'll get 3x squared. We multiply both sides by the dx, and we divide by 3 because there's no 3 here. We get this as our full expression. So I'm going to take that x squared and that dx, and I'll replace it with 1 over 3 du. And I'm going to take this to be u, so 1 over u du. And then from here, I'm going to go ahead and, oh, I forgot the 1 over 3. Excuse me, I was going a little too fast. So 1 over 3 ln of u, and then I have 4 to 2, and then I plug in back that u expression. X to the power of 3 minus 1. And I'll put in 4 and 2 back respectively. This step I did skip over here because it was a bit easy just doing your head, but I'm going to do these out loud because I don't want to mess this up. So I'll do 4 to the power of 3 minus 1 and minus ln of 2 to the power of 3 minus 1. 4 to the power of 3, that's going to be 64. So 64 minus 1, that's going to be 63. And then 2 to the power of 3 is going to be 8. 8 minus 1 is 7. So ln of 7. All right. Last one of these. Let's do u to be x squared plus 1. And then du is going to be 2x dx. From here, I can, I don't see the 2, so I'm going to take it out. And I'll use this on the top to substitute this, and this on the bottom to substitute those two. So I get nothing but u's. And I'll have 1 over u du, which is just, oh, I forgot. I keep forgetting the fraction in the front. My bad. ln of u from 3 to 1, and we plug in back u. X squared plus 1. For this, I will skip the step of doing it like this, just to be straightforward. 3 squared is 9, plus 1 is 10. 1 squared is 1, plus 1 is 2. And that's it. That would be your final answers. Now again, if you ever have the concern of what you did was incorrectly, from here, before you plug in these values, you can just simply check. You can go, okay, what's the derivative of this? You know, you would write as 1 over, and then they would chain rule. What's the derivative of what's inside? 2x. And then you have the 1/2 in front, so the 2's would cancel out, and you're left with that x. And you can do the derivative for all these guys. Now, let's do inverses that have integrals that have inverse trig functions. Now, recall the idea of the trig functions and their inverses. This does not equal 1 over sine of x. Its inverse in that technical notation of f of x and f inverse of x. So please, please, please keep that in mind. So that means you go backwards. So for example, an angle that gave us square root of 3 over 2, an angle that would be 60 degrees, or you would say, it's pi over 3. For here, 1/2, but negative, that would be on the other quadrant. So you would say, you would say 2 pi over 3. -1, where they both equal, but one side's negative. That's going to be 3 pi over 4. Over here, that's going to be pi over 6. Here, cosine, so that's going to be pi over 4. And this guy is going to be, I know it's on the right quadrant, but what is it? I believe it's pi over 3 as well. Let me double check. Sine of pi over 3, cosine of pi over 3, that's going to be square root of 3 over 2, 1 over 2. Yeah, okay. Just double checking. Okay. Right. So from here, we know that these inverse ideas exist. Now, keep in mind the differences between these. We're not going to go too into depth with these. This is pre-cal material. If you need me to, let me know. Or if I need to link a video, just let me know. What we're getting into is seeing their expressions as derivatives and integrals. So recall these from your Cal 1. And then depending on which Cal 2 you took, you also saw these. If you took mine, you saw these. If you didn't take mine, then you didn't see these on the right. So the key idea here, I do want to color code this for a little, is that you have the constant included in, and then instead of 1, you have an arbitrary a. And the a will play into an effect right here. So keep this sort of visual in Q. Now, granted, you'll have these formulas during a test, but you just have to puzzle piece. So, for example, this integral. We see that there's a 3, so that constant can be just present, and then we see a square root. So we have 2 that have a square root. And we see that within the square root, there's a square subtracting another square, with x being the specific square. So that means that we have to use one of these. What's the difference between these? The usage of the negative. There is no negative here, so we're using this guy. So this is just going to be 3. You can say arc sine or sine inverse of x over what this was. Well, this is squared, so you would say 2. And then plus c. Over here, you have the exact same thing, but this time it's 16. And 16 is what squared? 16 is 4 squared. So x over 4 plus c. Over here, you don't see a square, so you can just freely use this. We have 5, and then times tangent inverse of x over 4. But what am I missing? Well, I'm missing that this time the constant also has a divided by a. So we divide that by a. And then lastly here, we see that, oh, I forgot to tell you. Okay, so these got swapped, but we know that addition is commutative. 2 plus 3 is the same thing as 3 plus 2. So we can just mentally rearrange, well, I should have said it here, that's my mistake. But mentally, we could just rearrange these so it closely matches that. And we get 3 over 3 times tangent inverse of x over 3 plus c. Which in reality, that can get simplified to tangent inverse of x over 3 plus c. So a bit of an extra step, but not a criminal step. All right, so that's going to wrap up Unit 1. This was sort of a review because nowadays most Cal 1 classes do cover integration. I'll be honest, when I took Cal 1, it was just derivatives. We only did derivatives. And then when I did Cal 2, we jumped into integrals. But nowadays, like if you take a Cal 1 class, probably within the last 10 years, you'll probably have done it this way. Um, Maybe not 10 years. Maybe 10 years is a little too long. But okay, we'll say 5. If you took a Cal 1 class within 5 years, chances are that Cal 1 class had integration built in. But if you didn't, then it did not. And your Cal 1 class had it. Or I think I butchered that. Let me say it again. If you took the Cal 1 class within the past 5 years, you probably went over integration. If you didn't take the Cal 1 class, maybe took it over 5 years ago, chances are it didn't include integration. So make sure you fully go through this. Okay? Alright, that's going to wrap up today's lecture. I'll see you all in the group work video. Bye-bye. Oh, well, not bye-bye. Real quick, random. But I've been playing with this fidget. It's kind of scary looking. Look at the snake. And it has glass eyes. That's it. Alright. Okay, now. Bye-bye.